Let's do a quick example of using the squeeze theorem, and then I want to show you some pitfalls if you think you can get around using the squeeze theorem. So just to make things simple with inequalities, I'm going to look at a limit as x goes to 0 from the right, so x is going to be positive. Just makes it a little easier not to screw up with some inequalities and minus signs, because that's the one tricky thing about inequalities. So here's a fairly complicated function, x times sine of 1 over x squared plus 17x. This is not something that's really nice algebraically. And so it would be very hard to use some sort of algebraic method here. But I claim that the limit is actually just 0. If you look at the picture, this is a pretty tame function away from the origin. It gets a little wacky here. You can start to see some really dense wiggles, but the size of the wiggles seem to get small. And that is suggesting that maybe the limit actually is equal to 0. Okay, so we're going to squeeze it. Here's the key, and a lot of basic problems with the squeeze theorem are based on sines and cosines, because sine itself is, I guess, what we call sandwiched, that it's always between minus 1 and 1. And the key is that it doesn't matter how complicated the input of a sine function is when you're just quoting this result. The sine of any angle whatsoever is between minus 1 and 1. How does that help us? Well, we're dealing with something that's a very small modification of that, namely that times x. So one of our basic things we can do with equalities and inequalities is multiply both sides of an inequality by the same thing. So let's multiply that thing by x on all three terms there. And note, here's where it's nicer going from the right, that since x is positive, none of these guys switch. So x sine 1 over blah, 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 that's our g of x, is between minus x and x always. Actually, and it really is always here, not just near 0. Or at least when x is positive, of course. All right, so we've got our f function, minus x, our h function, x, and we're ready to go. Those are simple functions. We know their limits, and if we look at the picture, we can be reminded that those things, those bold lines, are both going to 0, the same value as x goes to 0 from the right. And you can see the squeezing start to happen. Let me zoom in a little bit. Got one that's zoomed in. So here we're only going to like 0.05, and you can see this function is complicated. It wiggles, and the wiggles get denser, but at the same time they get smaller, and so the limit does exist, and it's going to be 0. All right, so how do you write that down really carefully? We know that the relevant limit of f minus x and h, x, those are both equal to each other. They're both equal to 0, and therefore the squeeze theorem applies, and so this function that's trapped in between and squeezed in between also has limit 0 as you go to 0 from the right. Turns out the limit is 0 from the left as well, but you just have to be a little careful about the inequalities. So something Stuart points out that I like, and I want to give another example of, is a pitfall could be, if you've never heard of the squeeze theorem, or if you don't want to use the squeeze theorem, you could be like, no, it's way too complicated. The limit of a product of two things should be the product of the limits. Okay, limit of x times sine blah, blah, blah is limit of x times limit of the sine. Limit of x is clearly 0, which is a fact that we actually just used, times, yeah, whatever. Again, they would say, yeah, the great thing is I don't need to know the limit of this thing, because 0 times anything is 0. Problem is, when you use this law that the limit of a product is the product of the limits, both of the limits have to exist individually. And this second limit doesn't exist. That is something that has infinite wiggles and does not get smaller. You might think, though, well, I got the right answer. There must be some way to make this work, or maybe you're just being too picky. Okay, well, suppose we change that just a little bit. Suppose it was like x cosecant 1 over x squared plus 17x. Somebody tries to use the same reasoning. This limit times this limit, 0 times anything is 0, and they're like, well, so, should be right. And maybe I'm not being super careful, but why isn't that right? Well, it's just not actually true. At first, if you look at the graph, they might be trying to convince you, as the skeptic, that it's true by looking at the graph. That actually does look, right here, that it looks like the limit is going to be 0. But look at this big scale here. That's a little suspicious. Okay, maybe that's hiding something. And, of course, we really care about what happens when x gets really small. So somewhere in here, there might be something hiding. And, of course, we're also using a calculator graph, which sometimes can just totally miss the point. So here I've zoomed in, and we discover, oh, everything just goes to heck at near 0. Instead of having this nice sort of quadratic kind of decay, you start including asymptote, asymptote, asymptote. You actually have an infinitely dense accumulation of asymptotes near x. That's almost the worst kind of limit I can imagine is that x goes to 0, you keep encountering all these kinds of numbers that will keep blowing up to infinity over and over and over again. And so that's a case where this reasoning not only is bad reasoning, it just absolutely is utterly misleading. The limit here does not exist in a horrible way. And so that shows you, I think, a little bit more powerfully than Stewart's example, how this is just not legal. So, and that's one of the motivations. Why we had a better method using a different tool that wasn't about algebra, that was about inequalities. The Squeeze theorem totally told us what this first example was going to be, and it worked. Oh, and why doesn't the Squeeze theorem work? Just to finish off, why doesn't the Squeeze theorem work in this case? Well, cosecant, that has asymptotes in itself. That's really the source of the problem here. Cosecant of theta, that's definitely not between -1 and 1. It's not bounded at all. If you remember or just look up the graph of cosecant, that does not have this wonderful sandwich property. Where was that? That sine did, which was key to using the Squeeze theorem in the first place here. All right.